אנחנו שמחים לארח את גלעד יהודאי, כרגע פוסט-דוק ב-NYU, לפני כן עשה את הדוקטורט בוויצמן. גלעד זכה בכל מיני פרסים, כולל ציון לשבח מבלמטניק שלנו, והוא יספר לנו על שאלות בתיאוריה של Deep Learning.
You speak in English? That's okay? Okay. So I'll talk about two lines on deep learning, data reconstruction and transformer structure. There's a bit of delay. Okay. Great. So you probably heard about the deep learning revolution and recently LLM revolution in recent years. Deep learning LLMs can do many wonderful things. For example, they can generate images, they can generate text, we can chat with the chatbot, ChatGPT, Gemini, etc. They work for autonomous driving, they can solve different problems related to biology, chemistry, molecules, etc. But there's a problem with, every time I click, there's like 3 seconds delay. So I try to click 3 seconds earlier. There's a problem because deep learning theory lags behind, like this slide. So we usually look at it as a black box where there's an input and output, and we don't really know what's happening inside. And we look at it as theoreticians, we look at it in a small flashlight, trying to understand in simple models, under simpler assumptions, how it works. And it's interesting to understand why it works, when it works. There are many reasons for it. For example, practitioners know how to make neural networks work. And it's great when they work, but they don't know why. And when they don't work, it's terrible, and they still don't know why. And theoreticians try to provide some theoretical explanation for some of the phenomenon or some of the problems that practitioners tackle in practice. So in this talk, we'll talk about 2 challenges, not necessarily the largest challenges of deep learning, but 2 pretty interesting and relatively large challenges I'm interested in. One of them is memorization and reconstruction, how neural networks memorize. And if they do, can reconstruct or understand what they memorize. And the second problem is about expressiveness and design choices. How can we make smarter design choices for machine learning models in general? Let's start with memorization. And I want to give a very, very simple machine learning, standard learning setting. So in general, we usually have a data set, X's and Y's, inputs and labels, and we have a model to optimize. This model can be, for example, a neural network, transformer, this kind of model, and a loss function that we try to minimize. And what we try to do usually is to find a solution to this empirical risk minimization problem, or to minimize the risk of the model or of the inputs, the data set, according to the loss. And when we talk about memorization and reconstruction, there are a few questions we want to ask. The first one is, are the data samples Xi somehow memorized or somehow encoded inside the weights of the model? So I call them the weights theta, and are they memorized inside? And if they are memorized, can we reconstruct them? Can we somehow extract the data itself just out of the weights? And if we can, is it related to the specific method that we use to solve this minimization problem? Because I haven't said how we solved it, but in practice, people use very specific ways to optimize machine learning models, right? You use gradient-based optimization, gradient descent, SGD, ADAM, and is the method that we use related to how the model memorizes? Yeah.
When you say solve, what do you mean exactly? Do you mean finding a local minimum or global minimum, or just a point that has a low value without knowing that it's a minimum?
So this is still high-level talk, but I mean we try to optimize this problem using gradient descent. So people usually try to find a global minimum, but the local usually, but yeah. So or a stationary point in general. And the second issue that I'm interested in is about architectural choices, and specifically in this talk, I'll talk about transformers. So this is like a basic transformer block. It may look complicated, and it is, but what I want to say, you don't have to really understand it, but in each of these blocks, there are many design choices that people have to make. And it's not usually clear how to make them, and even sometimes these design choices are interdependent. So if we choose one of them, it kind of restricts another block or another option that we must choose. And many of these choices that people make are defaults. People sometime in the past, just decided that these are the good parameters which you choose, and they persist only because earlier models use them. And in this talk, I'll give an example of a default parameter that people use just because someone decided it was the default. It has some interdependency, and it's not always the good choice. There are cases where it's actually a very bad choice to make. Okay, so these are the topics that I will talk about in this talk. My research focuses on a couple of topics, mostly related to theory of machine learning, but has connections from or motivation from the practical side of machine learning. So one topic I'm interested in is attacks on neural networks. One of them is reconstruction attack, which I will talk later on. Another is adversarial examples or adversarial attacks. When we add a small noise to an image, it completely fools the model. I will not focus on this in this talk. I'm also recently interested in the theory of transformers. And during my PhD, and also recently, I studied the theory of deep learning, where I like to split into three pillars. The one is expressiveness, what models can express and how can they do it efficiently. Optimization, how to train them, or to give some guarantees on training machine learning models. And generalization, how can models generalize to data which is unseen during the training. In this talk, I will focus on a few works about the reconstruction and one work about the theory of transformers. So this is the outline. Let's start with the first one. So first of all, I want to provide some motivation on why data reconstruction and memorization is interesting. First thing is that when we train, let's say we train a neural network, a very simple neural network, just to classify dogs and cats. And if the network actually memorizes the images inside the weights, we want to know about it. It's some phenomena that's interesting and want to know when it happens and why it happens. So this is more of a, let's say, understanding a phenomena kind of question. But it's also interesting in the sense of privacy, because if we have a reconstruction algorithm that we can take a neural network that was trained on some data set, maybe a sensitive data set, and we can reconstruct the data just by knowing the weights, this data can be confidential. It can be confidential images, credit card numbers, and many other kind of confidential data. And we want to know and want to protect against these kinds of attacks, and it's interesting to know whether these attacks exist. So let's move into data reconstruction. And I will start, before going into data reconstruction, I will start talking about generalization in neural networks, and we'll see how it connects to data reconstruction in a few slides. So classical learning theory suggests that models should not be more expressive than necessary. This is known as Occam's razor. And for example, here, if we take a data set, so here the points are the data set, and they are generated from a degree 3 polynomial with some noise. And a degree 3 polynomial, which is this line, kind of captures the essence of the data, but it doesn't fit the points exactly. If we try to fit them with the degree 8 polynomial, which is this wiggly line, then it exactly fits the data, but it doesn't capture the essence. And this is a phenomenon known as overfitting, which we expect to happen when we have more parameters than training examples, much more parameters. So this is known as the overparameterized regime, and we expect overfitting to happen, but what happens in practice is that neural networks usually don't overfit. They can generalize well, even if they are over-parameterized. They have much more parameters. And this is one of the major questions in machine learning theory, why neural networks generalize so well. And I will give some kind of explanation. Where the slide? So one possible explanation is that adding explicit regularization, like L2 or L1 regularization, may lead to simpler solutions. But this is not a good explanation. So it was shown in a very interesting paper from 2017. It was called To Understand Deep Learning, We Need to Rethink Generalization. And they showed that neural networks generalize even when they don't have explicit regularization. So why they do generalize? One explanation is known as implicit regularization or implicit bias. And what happens is that when we train neural networks, we use a very specific method to train them. We use gradient methods. And it is believed that gradient methods lead to very specific solutions that actually not only solve the optimization problem, but they also generalize well. So these are kind of the good solutions that we get to when you train using gradient method. And to put it more formally, what do I mean by good generalization? I'll give two examples. So the first example is for logistic regression. It's maybe the simplest learning algorithm. And if we take a linear predictor, just W times X, and we train it on a separable data set with logistic loss and gradient descent. So logistic loss is just the simplest possible loss for classification. It's equivalent to binary cross entropy. What we get is that this predictor converges in direction to the solution of the max margin, which is minimizing the loss, minimizing the norm such that we classify the points, each point correctly with the correct label and with a margin. Here it's a normalized margin of 1. So why this theorem is interesting? If we think about a binary classification concept, which is separable, think about two clusters. There are many different lines that can separate them, right? This line, but only one line is the max margin, is the one that maximizes the margin between the points. And this line also generalizes as well, because if we think about data coming from the two clusters, then generating a new point will just with some, if we think about some distribution, then with some larger probability with the max margin solution will be classified correctly. So this is in some sense the best solution that we can take. And this theorem says that because we train with gradient descent, we get to this max margin solution. Okay, so this was about logistic regression. What happens? Yeah.
So question. I can maybe understand or think that I understand why it converges to the max margin, but why does it also converge to something with the minimal norm?
Okay, good question. So the max margin is the dual problem of the minimal norm. So when you think about, let me write it down. Can you see it? If you think about the max margin, you want to maximize over the xi, the minimum over w, which is w times xi, yi, such that the norm of w is equal 1. That's what you're looking for. That's the max margin that you know. Want to minimize the margin over the maximum over all the points. And the dual problem of this is exactly this. So we get, that's the dual problem. And it's easier to work with this problem because we don't have a min-max optimization problem. We have just a minimization problem with inequality constraint. So it's the same thing. That's a good question. All right. So let's move on to neural networks. So for a neural network phi parameterized by some parameter vector theta, under some technical conditions that I'm not going to specify exactly here, if we assume that the network perfectly fits the data, then again, gradient descent with logistic loss converges in direction to a KKT point of the max margin problem. And here this max margin problem is almost similar. We have to minimize the norm of the weights such that the output, so here instead of W times X, we have the output of the network is classified correctly with some positive margin. And the KKT point is a stationarity-like point for constraint optimization problems. So here we have a constraint optimization problem. We want to minimize something under the constraint that this term is larger than 1, then KKT is just a classical way to solve this problem. And this is a very interesting theorem, and I'll show why. It's one of the, for me, it's one of the cornerstones in recent years about machine learning theory, because it gives us some characterization of what a network, how a network converges on, what it converges to after training. And this is something that's pretty difficult to achieve, but here we have some characterization for it, and we'll see what we can get from.
What's the technique? Very complicated technical assumptions or simple ones?
Okay, so for this theorem, the technical assumption, the main one is that the network is homogeneous. So if we think about a two-layer neural network, it can have ReLU or some homogeneous activation and bias only in the first layer. But there are a few other like follow-up works that are like a very long line of works that lacks these assumptions to quasi-homogeneous with residual connections, and there's like a long line of work on making these technical assumptions more relaxed. So what are the KKT conditions? We know that this is just from the previous slide. The neural network converges to a KKT point of this minimization problem. And the KKT equations or constraints say the following thing. There are lambda 1 until lambda n, one for each data point, xi, and satisfy the following. First one is that the stationarity condition, the theta should be a weighted sum of the gradients of the network at the point xi, and they are weighted by these lambdas. This is a very interesting equation because it gives us a characterization how theta should look like given the data. And it's interesting to know how the network, how the weights will look like if we know the data. And the second one is known as complementary slackness, which means that this lambda is equal to 0 if the point doesn't lie exactly on the margin. This means that if a point doesn't lie exactly on the margin, it doesn't affect theta. So theta is affected only by the points of the margin. This makes sense also in the support, the SVM, which is support vector machines, where the classifier is affected only by the points that lie exactly on the margin. So this also works as well. Okay, so after this long introduction about generalization, let's move to reconstruction. How can we reconstruct data given what we know about this implicit bias? So the stationarity condition provides a relation between theta and x. Usually when people looked at it, they said, okay, we know the data, we know how the data set looks like. What can we say about theta? The novel technique or the novel point of view that we had is to do the opposite. Said, okay, let's say we have theta. Let's say we know how the weights look like. Do we know how the xi look like? How the data set behaves? And for that, we define the data reconstruction loss, which is just taking the stationarity condition and trying to minimize it. Just taking theta to the other side and trying to minimize the L2 norm. But note that we minimize, we assume we know theta, and we minimize over the xi's and the lambdas. We also don't know the lambdas. We're trying to find a data set that best fits the given network.
Again, the lambdas are not part of the data set. Only the data set is X, right?
Right. The lambda is not part
the lambda just hidden parameters that you find along the way.
Exactly. We don't use them. We have some follow-up work that we try to understand what they mean, like how each point affects the weights given the size of lambda, but they're not part of the data set. Yeah.
What about the Y's? The Y's is the output for this.
Good question. Yeah, so we don't know the Y. So what we can do, first of all, let's say we know it's a balanced data set, half and half. So one class and the other class, so we can just set them this way.
Oh,
Another way.
It's classes, yeah.
Yeah, it's classes. if we don't know, let's say we don't know how they are balanced, then what we do here, we don't set n, like we don't just initialize n data points, we initialize much more data points. Let's say we know that the data set was included 500 points. So we try to reconstruct 2,000 points, like much more. And then we can split it, the y's to be even. And even if the data set is not balanced, it will still be okay. Exactly, it will be balanced. And some of the xi's will not be reconstructed well, but we can throw them away and just take the good one. And in the next slide, I'll show you how we actually reconstructed the data. So by complementary slackness, we know that if some point doesn't lie on the margin, its lambda is 0, and we cannot reconstruct. So this method can reconstruct only points that lie exactly on the margin. Okay. So I want to show you some results about how we construct the data. These are actual reconstructions. We took the CIFAR10 data set. We split it into two classes, animals versus vehicles. There are 10 data sets, but we split them into two. And we use just a 3-layer MLP. And the data set included 500 samples, evenly between classes. And as you can see, we could reconstruct the samples pretty well. They are still a bit noisy, but the essence of the data is actually constructed. We can find the actual points, the actual images that were on the data set. This is from a paper from 22. Any questions about?
Very nice.
Yeah.
How would you go about like generalizing it to like bigger learning problems and like harder tasks?
What do you mean by other tasks?
If you give it like ImageNet, not CIFAR10, how would you
Yeah, so we had
generalize the approach?
That's a good point. So basically, this reconstruction method doesn't take into account, the size of the model, right? Just based on the implicit bias, which is correct, at least, for every model that was trained under these assumptions. We did have technical difficulties with larger models. So we had a follow-up work where we reconstructed exactly images from ImageNet or ImageNet-like dataset, and we used a different regime, which is kind of transfer learning or fine-tuning regime. But yeah, there are still many open problems about how to make this attack stronger, how to generalize it. It's still not it's not perfect, as you can see. Even for this kind of small data set, the reconstructions are not perfect.
Would you consider self-supervised objectives and how maybe the margin there is less of a problem because the network decides on the boundaries per class, so maybe you can have access to more training examples?
We haven't, but when you say self-supervised, so there are samples that doesn't have labels. Right. I'm not sure whether the max margin theorem will work on this setting, but we can test it empirically. But we haven't gone through the section.
I don't have feelings if the images were just IDs and we really care about the numbers, the ID numbers, how it will be doing there.
You mean like the images are just vectors? You think about them as vector numbers?
The social security numbers.
So there will be noise, a bit noisy.
There'll be noisy, so it will not be exact the numbers, but there'll be
some
numbers will be correct and some.
Yeah, but even the ones that are correct are not exactly the numbers. There will be some noise. The benefit of images is that if we add some noise to an image, it still looks like an image.
Yeah, I just wanted to see if we still save somewhat. Even
yeah. So it's not.
Maybe I missed something, but do you assume anything about how well the networks learn these samples?
How they generalize? What do you mean by learn?
No, I mean, do you assume that they memorize these instances or?
So all I assume is that the network, the assumption of the implicit bias theorem says that we assume that the network perfectly labels the data set. And it reaches a KKT point, which means that it trains for a pretty long time. So in practice, let's say this network also generalizes well. So I'm not sure how to measure memorization. That's a good question in itself. But in some sense, the network did memorize the data set that it received 100% accuracy on the entire data set.
What happens about the points that are not on the boundary, those that you cannot reconstruct?
Yeah, I don't know. We cannot reconstruct them. So, for example, in this data set, we reconstructed about 50 samples out of the 500, and the others one were noise. So, in some sense, these points are protected, at least for this attack.
But the majority cannot be reconstructed.
Yeah, but there's another question of which points lie on the margin. Maybe we can remove points from the margin or add points to the margin, affect the margin somehow. But basically, at this attack, we cannot reconstruct points from the outside of the margin. I think it's a general question of whether there is enough information to, with any attack, reconstruct points outside of the margin. I'm not sure there is enough information in the weight of the network in terms of the information theory, visual information between two data.
Can you show again the problem that you solve in order to get the image?
Yeah. So this is taking the stationarity condition, just putting L to null.
So C theta and Xi is just a satisfaction.
Yeah. So phi of theta xi is the output of the network. When we take a gradient with respect to theta.
So how do you not take the gradient? Just compute it again, or what?
Yeah. I assume that I know the network, all the weights and the structure of the network, so I can take a gradient with respect to theta, and at each iteration, I don't know the xi, but at each iteration, I take a gradient with respect to theta, and yeah, given the xi at this iteration, I calculate the gradient.
Then you try to minimize this, or what?
Yeah, I minimize this. This is the loss that I minimize.
How difficult is it? It depends on how complicated it is. No?
It's a pretty difficult problem. I agree. It's not an easy optimization problem because this term is pretty difficult and the xi is inside the gradient. I didn't say it's an easy optimization problem. I didn't promise that. But it's a difficult optimization problem, but we can solve it.
So you assume what? It's a linear in the xi?
No, it's a non-linear in the xi because phi, let's say it's a neural network with radio, and then you take a gradient of it, so it's a pretty complicated function. Yeah.
So do so.
This optimization problem, let's describe in this hand.
Like which one?
Yeah, how do people train neural networks? They don't have any guarantee, but they still train pretty good neural networks. It's the same. I agree. I don't have guarantees for why it converges, but I can show you like the images that it did converge. But I agree. So there are at least recent works by other groups that try to give some kind of guarantees for this optimization problem or to show that the solution is unique. But there are many open issues about this, but we can show in practice that it works.
So the gradient is towards the xi's. That's what you do now. The gradient in sense.
Exactly. I'm training the xi's, not the theta. That's the reverse way to think about it.
So you have answers?
You had a question?
Achla.
You don't have any kind of guarantees that ensure that you will find the correct
Yes, I don't have, but there are like new results from this year that show that under some conditions there is uniqueness. But again, I don't know for safer other some.
But you could find also fake solutions like XI that.
Theoretically, I could, but I don't.
I didn't find any fake solution.
What is a fake solution?
That's something that is not in the training set.
So I don't know. I found a lot of noise, but I also found good images.
Okay.
I don't know if the noise is a fake solution, but given that I found a good solution, maybe there is some implicit bias, not for neural network, but for this problem that leads it toward good solutions. But that's good. Okay, so I don't have too much time. I wanted to talk a little bit about some follow-up work. So we had quite a few follow-up work for this work. I'll just do this one briefly. The first one is we want to extend this reconstruction to new regimes and to understand more in depth what makes this reconstruction possible. So we extended it to other regimes, multi-class regime, convolutional neural networks, and to other losses, regression losses. And about what makes the reconstruction possible, there are many different aspects. One of them is the relation between the number of samples and the number of neurons. And there's like a positive correlation. If we have more neurons or more parameters, we can, and less samples, we can get better reconstruction. This kind of makes sense if you think about it, because the number of neurons or the number of parameters determines the number of equations, and the number of samples are the number of variables. So we need, if you think about the intuition from linear algebra, more equations than variables. So this is not exactly linear equations, but we have the same intuition. And we have some other follow-up works, one about transfer learning, that I'll skip, and another one about reconstruction from group invariant networks, but I'll skip it. And there are many different questions about just this aspect of reconstruction by our group and other people from different groups. And it's really interesting. Some future directions, one of them is to reconstruct in other realistic settings, for example, transformers and LLMs. I think the problem with, there are many problems when we try to reconstruct from LLMs. One of them is that we don't know what is the implicit bias of LLMs. There are some works that try to do it. I'm also working on understanding the optimization for LLMs and what is the implicit bias, but it's a question in itself. And characterizing the implicit bias.
What is implicit bias?
So characterizing some condition on the weights after the network is trained. Finding some bias that, like the weights of the network are biased towards certain solutions. Like here we had the max margin, they are biased towards max margin. But what happens for transformers?
So you assume like any like approach has some implicit bias, maybe we don't understand.
Yeah, there is some implicit bias.
Simple implicit bias.
That's it. Yeah, we don't understand. We have some understanding it's related to the max margin, but it's structured a little bit different.
In principle, the speculative conditions could apply to transformers are also trained with.
So if you think about autoaggressive training, they don't satisfy the conditions because they're very non-homogeneous. That's the problem. Yeah, and we try to classify like a different set of. It's pretty difficult. Okay. So to conclude, I think that understanding this implicit bias, not just in relation to data reconstruction, in general, reveals a lot of phenomena or helps us understand a lot of phenomena related to deep learning. For example, adversarial examples. Some works that I did is about adversarial examples, benign overfitting, or procedure called machine learning. And there are many different aspects of neural networks that we can understand if we know what is the implicit bias.
And how does it relate, sorry, for the reconstruction? Why reconstruction will let you understand the implicit bias?
Because if we know the implicit bias, we know that the stationarity condition.
No, the other way around.
What?
How with reconstruction? I thought you were saying that reconstruction will help you to understand.
No, the other way. If we know the implicit bias, we know a lot of. So for the second part of the talk, I'll move on from implicit bias. And we'll talk about the expressiveness of transformers and some design choice. I'll give a brief intro into transformers. The next slide will be a bit more technical, but this is just for like high-level intuition. A transformer is a sequence-to-sequence model. We have an input sequence of tokens for an input. You can think about these tokens as words in a sentence, or just, I like to think about them as just vectors in RD. And the output is also a sequence of the same length and of the same dimension, usually at least. And inside the transformer, there are two main mechanisms. The first one is a self-attention, and the second one is just a feed-forward neural network or an MLP. So this one is standard. The self-attention mechanism, what it does is it calculates for each token how much it should attend to all other tokens. For example, if you think about a sentence, so the word it calculates how much it should attend to each other word in the sentence. And the self-attention does it from every word to every other word in the sentence, or from every token to every other token. It's like an all-to-all calculation. And to put it in formulas, we can write the self-attention layer the following way. So we have a sequence of tokens, x1 until xn, where each one is a vector. And we have the attention is a sum of age attention heads. Each one looks like this. So we have a key and query matrix. Each one is multiplied by x. And then this part calculates the self-attention. And then we get a score. And we use softmax to normalize this scores into probabilities. So here we have the probability after the softmax of how much each token should attend to every other token. And this is multiplied on the outside by x again, and by a value and output matrices. So this is like the basic, maybe the most basic attention mechanism. And what is interesting to know for this part of the talk is that all of these matrices are in R and R times D matrices, when R is much lower than D. So this is the input dimension, and R is some so much lower dimension that the matrices are in. So if we multiply K by Q, we get a D by R times R by D. We get a D by D matrix, but it's a rank R matrix actually. And what is a transformer? So a transformer is just stacking these self-attention layers. In between, we have MLP layers, these feed-forward networks, and normalization layers. So this is maybe the most basic building block. There are many different other gadgets that people use, residual connections, and many other stuff, but that's the basic. Okay, so when I talk about design choices, there are many design choices that people who construct transformers have to choose from. For example, they need to choose the number of heads, right? Where the sum over the number of heads. They have to choose the rank, the input dimension. They also have to choose the depth of the transformer, the size of this MLP, the depth and the width, which normalization layer to use. And this is a very, very non-exhaustive list. There are like many different parameters that people use. And in this talk, I'll just focus on these three: the number of heads, the rank, and the input dimension, and the connection between them. So to talk about why people use them or how people choose them, I'll give you a brief introduction to some experiment that people did. That's not my paper. It's from a pretty known paper about in-context learning. And what they did is the following experiment. They sampled a line, think about a high-dimensional line in any direction, and then they sampled points that lie on this line with some noise. And they inputted these points into a transformer and asked, what is the line that these points came from? What they actually wanted to do is to teach a transformer to solve the linear regression problem. So this is some experiment that they did, and they also have to make these design choices. And they had to choose the number of heads, and the number of heads that they chose was 8. Why they chose 8 heads, I don't know. So that was their choice. But what we did is we took the exact same experiment and we changed the number of heads. We think, right, if we add more heads, it's going to be better, right? More heads going to perform better. So we redid the experiment and we had the exact opposite results. So the number of heads was 8. If the number of heads was 8, that was the result. This is the mean square error, so lower is better. And if we add more heads, the performance was worse. And it actually performed pretty well when we have just 1 or 2 heads. And we wanted to understand why. So it's kind of like the opposite of the intuition that we should have. And the reason is related to how people choose these parameters, H, D, and R. So let's see how people choose them. The first paper about transformers was called Attention is All You Need. And they also have to choose these parameters exactly. So they choose D to be 512, R equal to 64, and H equal to D over R. So why they choose, so here D over R is 8. Why they choose this scaling? They had 2 reasons. The first one is that the total number of parameters is fixed if we change R. So if you think about R equal D, we have just one full rank matrix. or R equal 1, we have 512 rank 1 matrices, the number of parameters is exactly the same. So this is one reason. And the second reason, which is a bit interesting, is that it worked for them. And they have a paragraph in the paper where they say, yeah, it works well for us, and let's keep with it. And people thought about it a lot, and they just kept the same scaling for pretty long time. So in like many models after that, they chose also almost the same scaling, D over R. But what happened is that D became larger, like 10,000 and more, and R was kept small, 128, something around this. And if we look at okay, so I'll go to address in a second. So the question I want to ask is, we have basically two options here. We can have what people did is they choose many different, many heads, which are small, low end. But another option, which we saw before, is choosing just a few heads, one or two heads, which are stronger, which they have like more higher rank. And the question that I try to ask with the Hydra is, which one is better, like high rank, a few high rank heads, or many low rank heads? And if I go to the experiment before, this is the exact same graph, I just changed the x-axis, and we see that there is a rank deficiency problem. Because if we have low rank, then the results are not as good as having higher rank. It doesn't matter like that we have fewer heads. And in this work, we wanted to prove it formally. Wanted to show that we can pay a bit for rank and save a lot of heads. So to do it formally,
on the previous picture, with the rank, you had a fixed number of heads.
Yeah. This is exactly the same picture, but I changed the x-axis to the rank instead of the number of heads. So we try to find some target function that is difficult to approximate with low rank, but easier to approximate with high rank. This target function is based on the nearest neighbor function. So nearest neighbor is think about high dimensional points, and we try to find the waves of soft one, and we want to find function the target point that is closest to this one. And let's say all of them lie on the unit sphere, so it's kind of a high dimensional problem. And our goal is to find some target F that is approximable by polynomially many high rank heads, but not even with exponentially many low rank heads. And this function is based, as I said, on the nearest neighbor function. So given x1 until xn and y on the unit sphere, we define the bias nearest neighbor as this argument. So if I delete this bias, this is exactly the nearest neighbor because they're all on the unit sphere, but I add some bias. And the target function is just a linear combination of these bias nearest neighbor functions for some choice of these biases and coefficients. So we have two main theorems, an upper bound and a lower bound. So the upper bound says that for any choice of points, the target function can be approximated up to any accuracy by polynomially many full rank attention heads. So if we try to approximate this target by full rank attention heads, we can do it pretty well, up to any accuracy. And the way to do it is if we set all the weights to the identity, think about where the key and query matrices, if we set it to the identity, we just multiply x by x. And we have exactly this, or x by 1, we have exactly the inner product, which calculates the nearest neighbor. And if you're worried about the bias, then we can add bias to the attention using positional encoding. This is also some technical addition that many people use. And to define the accuracy, there is a temperature parameter which determines how much the softmax is close to the hardmax. And if the hardmax is just, we calculate the argument. Softmax is some soft approximation of it, and if we're very close to the hardmax, we calculate exactly the target function. But since we have softmax, we can get very close to it as much as we want. Note that in this solution, the number of heads doesn't depend on the accuracy and on the number of points. So this is just a very clean solution for any number of points and for any accuracy. So this is the easier theorem. The more difficult theorem is the lower bound that says that even for the simplest case of n equal to, so think about, we have just 3 points, x1, x2, and y. And we want to understand which point is closer to y, x1 or x2. Then if we take a bounded one-layer transformer, where the number of heads is lower than exponential in d minus r, it fails to approximate the target even up to a constant accuracy. So here the rank need to be very, very close to d to get good approximation. If you think about r as being equal to d over 2, we still have exponential separation. We need r to be as far from d as a constant, not more than that. So this is known in the literature of machine learning as exponential separation, because we have one architecture that can approximate the target with polynomially many heads, and another that requires exponentially many. This works for a wide variety of potential mechanisms. And so here I talked about softmax, but it works for also a wider variety of mechanisms. There are many different mechanisms for attention, sigmoid attention, other stuff. The main restriction that we have is that they are bounded. But given that they are bounded, this lower bound is pretty strong in the sense that it works for a wide variety of mechanisms. I want to give some intuition on why it works. These are the two most technical slides in this talk. If I lose you, please come back in like 2 slides. Okay, so we can rewrite the nearest neighbor function by the argument of x times y plus a bias as just a sum of 2 indicators. Because the output, think about just x1 and x2, the output is either x1 or x2. And we have some condition when we output x1, some condition when we output x2. So just a sum of 2 indicators. If we assume for simplicity that x1 is orthogonal, exactly orthogonal to x2, then we can define this target f times x1. Recall that f is just a linear combination of these threshold functions. So if we multiply by x1, x1 times x2 is exactly 0, deletes this part, and x1 times x1 is just 1, because they're on the unit sphere. So this target psi is just a linear combination of thresholds. And what we do, the first part of the proof, is that we choose the aj and bj's, remember the biases and the coefficients, so that this linear combination will look like a periodic function, at least in some interval. So now, right, because if we have a threshold function, it looks like either 0 and then 1, or 1 and then 0, and then we can just play with the biases, so it will be periodic. So now we have psi, which is a periodic function, goes from 0 to 1 back and forth, polynomial size. And to put the lower bound, we have this lemma, which says that for any bounded function g and matrix K with rank R, the correlation of g and psi decays exponentially. I'll give intuition on why it happens. So think about g as the attention head. We try to approximate this psi with some attention head that is bounded and has a low rank. And think about k, just for the sake of argument, as being the 0 matrix. It has rank 0. So in this sense, G has no information about x1 and x2. It just knows y. If we look at the Fourier series of psi, it concentrates around a very specific direction. And this direction is x1 minus x2. So it concentrates around this discrete set of points in the direction of x1 minus x2. And G, at least in the Fourier space, have no information about x1 and x2. So the best thing it can do, it doesn't know this direction, can just capture some space in the middle. And this correlation, I'll just say that since we take expectation with respect to all possible directions, G should successfully get all the possible directions of psi. So the best it can do is capture some space in the middle, and this correlation with the target is very small, it's exponentially small. So this is the reason why we get exponential separation.
So this is very counterintuitive, right? Because Johnson Rubinstein tells you that you can project to a low-dimensional space and keep the nearest neighbor. So
Yeah.
where's the gap?
I agree. That's a good point. So if you, okay, the point is that we use a one-layer transformer. If you project it and do a linear combination of this projection, it's not, you cannot do it very well. What you wanted maybe to say that you can calculate, let's say, with some probability larger than half whether the target is closer to x1 or x2, right? And maybe if we take the majority, it's going to work well. But with a one-layer linear combination, we cannot approximate the majority. And this is what the Fourier argument says. So I'll just move to the next slide, which is exactly what you said. What happens when we add layers? So we can show that with 2 layers, we can do it. And this is a similar argument to what you said. If we take the case of n equal 2 and some epsilon larger than 0, then a 2-layer transformer with polynomial number of heads, let's say each one is just rank 1, can approximate the target up to an error of epsilon. How we do it? Exactly as you said, we take random heads, IID, we just project them into random directions, and then each one of the heads, remember, we just need to say whether x1 is closer to y or x2. Each head, in this case, will be correct with probability half plus something very small. And if we take the majority of them, they will be correct. And there is an open problem here, which is this works well for n equal 2. What happens for n larger than 2? And for n larger than 2, if we try to generalize this construction, then the number of heads will blow up with n. Not log n, it should blow up log n.
You have no dependence on R here for the number.
Yeah, because I choose R to be 1. I made it simple. Yeah. So it should grow at least, I think, linearly. I'm not sure logarithmically it will work. But just a second, I'll finish this point. And the problem is that if you remember the full rank solution, it had completely no dependency, not on n and not on epsilon.
Yeah.
So the open problem is whether we can find a low rank solution which is independent of n. And we have some experiment that says that it's not the case, but proving it was present.
Why does each projection succeed with probability 1/2? Because the size is independent of n or something like that?
No, just think about we have 3 vectors in high dimension. We want to understand whether x1 or x2 is closer to y. We project them to the dimension 1 with Johnson Rubinstein, which say that we lose a lot of information, but we still have like some correlation with the truth. So like the distances of the, let's say, the inner product is still correct.
If the n is large, if there are more than 2 points, and I'm allowed to scale with n, the size of the dimension of the projection, then I'm good, right? I can do it with high probability.
No, if you have n equal 2, if you have n larger than 2, then you need to calculate the majority. Like each one will be correct. The probability that each projection will be correct may depend on n, but the majority will still depend linearly on n. That's what we found out. Yeah. So that's some experiment that I'm skipping, and we're almost finished. So we try to prove. I'm also interested in proving separation for deep transformers. So this was like transformers that 1 and 2, and the challenge is to establish separation for larger depth. And the key insight that we saw is that depth for transformers provide the power to do parallel computation. And this is related to, we had 2 papers about it, one about the power of transformers to solve graph tasks. This is related to distributed computing. It connects to the, the MPC model, the massively parallel computation model to distributed. And with another paper about compositional reasoning with transformers, RNNs, and chain of thought, which is some kind of reasoning mechanism for transformers, And we also showed separation for deeper transformers, and we used a conditional separation based on circuit complexity low pass. Basically, TC0 not equal to TC1 and such assumptions. So to go to deeper transformers, we use different techniques, but it's also possible to do it. And few future directions. First one is that there are other hyperparameters in transformers that we want to understand. There are many different questions that we can ask. For example, other depth and width trade-offs, or the role of the MLP. Because if we think about the role of the self-attention and the MLP, then the self-attention is kind of the global computation. It calculates the attention between all the tokens to all the other tokens, and the MLP does a local computation. So what is the relation between them? Also an interesting question to study, theoretically and also in practice. And there are also other data types, because for this separation, we used an isotropic distribution. The distribution was like uniform in the unit sphere. You can also do it for Gaussian distribution, but this is very far away from text data. So how can we model text data? It's like a different question in general. How can we model text data? But given that we have some model of the text data, can we show separation for it? This is also something that I'm interested in working on. And to conclude, I think that the architectural choices that have crucial implications on the expressiveness of transformer architecture. It's interesting to understand how these choices that people make affect them. And finally, some long-term questions, let's say longer-term questions that I'm interested in. One is to provide theoretical explanation for empirical phenomena that people see in practice on transformers. And there are a lot of practical phenomena that practitioners study on transformers want to understand why they happen in practice, or want to understand a more in-depth understanding of transformers. For example, there's a phenomenon known as linear truth encoding, which we add some explanation for it. It's a phenomenon where the transformer has a global explanation of truth. Find some hyperspace that classify truth on one side and false on the other side for very different modalities, very different domains, but also the embedding structure. So, for example, transformer, people usually train the embedding. They don't use a fixed embedding. And it's interesting to understand what are the embedding structure of different domains, for example, or different languages, how they are moved from one language to another, or also the power of reasoning and how chain of thought help us solve different problems. And one, let's say, more high-level question is that in the theory of deep learning, split it into three pillars: expressiveness, optimization, and generalization. And it's in general interesting to study those pillars on transformers. I studied a lot of expressiveness. I'm starting to work on optimization, but there are many open problems also related to generalization, optimization, and still there are a lot of open problems.
So the work that you do on neural network is for classification, and for the usually it's about generating usage of the transformer. So your current theory is focusing on classification with transformer?
No. So it depends. We have different work. One of them, right, is for classification, but we have, for example, this linear reckoning work is for generation.
It's already for generation.
Yeah, and we try to understand like what happens in intermediate layer to transformer.
And just short, you mentioned by past that you have some work on unlearning.
Right.
How is it related to what?
So it's related to the implicit bias. If we know the implicit bias, this is related to the neural networks, not transformers. If we know the implicit bias, let's say we can take some point on the margin and forget it, remove it from the margin. This is the intuition. But technically, it's related to this stationarity condition and how we play with it. But that's yeah, that's it. Thank you very much.